Hello, everyone. Sorry, my battery was done. Let's see. Can you guys hear me?
Yes.
All right, great. Thank you. So you can hear me. We should be. We're recording. Recording. Share. All right, so we're back for the second part today. Um, I guess people are going to be coming in, so I'm going to be clicking that. All right, so I'll keep going. Please ask questions if you have any. So if you remember, and this is the second part, I'm going to be calling this neural input optimization with a train and frozen forward model. All right, and this is part two of that. So we've covered a lot. We're actually in a good position. All this background, I've already discussed a lot of this in the previous lecture. So here this should be smoother, but we left off at the constraint loss in our collab. So I was saying that instead of using torch MSE, now we're going to invoke this function constraint loss when we use it. So constraint loss takes in the wide pred vector, right? So that's going to be a vector of 3, wide target, vector of 3, a mask, which is a vector of 3 that we've talked about already as well. This vector is the mask. Okay. It's going to have an overshoot margin, which is essentially similar to having like in the clamps min and max for inputs or in the lower upper bounds for output. So you'll see how this can be used. We'll have weights to give strength to which variable we want to shift the focus on. So we can do that, and some kind of regularization weight. So remember that the loss value now is not just this, but it's so it's something that needs to be calculated overall and minimized. So it's actually going to start at 0. We're going to have a for loop, and every time that we're training a sample, this for loop is going to iterate through the vector of 3. So if you notice, we're going to do for I in range y pred. Remember that y pred is a vector that is 1, comma 3. Shape 0 would be 1. Shape 1 is 3. So because it's 1, comma 3. So that means that we are iterating through the 3 outputs, production rate, natural gas, flame temperature, something like that. So every one of those variables, it's going to get its turn to be analyzed in here in the loss. So the first step is going to be to select the weight that we want to give that particular variable, of the 3 variables. So that's why we have this weight over here. And you guys can play with these weights, as I said, constraint weights 1, 3, 1. So in this case, we indicate that this variable 2 gets the most strength. So that, first weight would be 1, then in the next iteration 2, and finally in the last iteration with the third element, the third value in the weights, these 3 values. Okay, so we grab the weight, and then we need to grab from the mask for each one of the variables what we want to do. So if you remember, we already talked about this in the previous video where we said the mask can be 1, 2, or 3. Do we want equality? Do we want greater than? Or do we want within range? So for instance, the last variable is a within range variable, but the other 2 variables are greater than, for instance. And you can play with these parameters as you see fit. Okay, so we essentially grab the mask. Let's say we're we're iterating, right? So remember, this is going to be, I is going to be here either 0, 1, or 2 for the three variables in y, in the y vector. Okay, so we are going to grab, let's say we're in the first one. So that means from the mask, we grab the first weight. And now, or sorry, so from the weights vector, guys, do you have a question? Question? Okay, so from the weights, we grab the weight for the first variable, 0. Let me do this. So remember that y is going to be equal, right? So there's A, comma, B, comma, C. All right, so we're optimizing all three, but we do it kind of in order. So we grab A, which is 0. Okay, so from the mask, we're going to grab I think it was the mask was 1. No, the mask was 2, 2, 3. 2, comma, 2, comma, 3. So when index is 0, right, we grab the weight for 0. We grab this mask, which is 2. Do you see that? So then we have that mask, and we look at the if statement, and we say if mask equal 1, okay, so it's not for that variable, so we don't do anything. It is, in fact, this one, right, 2. So this elif is the one that we run for that first variable. The next variable is 2, so that's also the one we run. And the last one is 3, so then we run this logic over here. Do you guys see that? So that's essentially how we can process this. Now, let's assume that the mask is actually 1, right? So let's start there. It's 1. So then in that case, the variable the if statement that we would select is this one, equality constraint. If you look, that is essentially an MSE because all we do is we have the model predicts a y pred, right, which is this one, and then we have a y target, which is the value that we're trying to be. So essentially for I, which is going to be the variable in question currently, so we're in this variable of the output A, okay, we are going to take the difference of that vector, square it, multiply it times the weight to indicate how much importance we give to this variable, and then add it to the loss. And that's it. That's my loss, essentially for equality. So if all variables here were 1, 1, 1, 1, then we would always just do essentially MSE. Do you guys see that? But we want to try other things, like we want to try 2 just greater than, but then we need some kind of overshoot margin. Or we want to try 3, which is something we already discussed, the softbox penalty approach. So now let's take a look at the option where the mask is 2 for any of the variables in the y vector A, B, or C. So in that case, we select this one here, okay? So mask is equal to 2, greater than constraint, okay. So how do we do that? We just need to emphasize that we want in the element in this, if you look at this, this is the exact same softbox penalty, but just the lower term. So if you remember when we did the softbox penalty, we had lower term part plus the upper term part, right? Here, because we only care about being greater than or equal to, we already discussed this in the previous video, we just do y target minus y pred squared, and then we run it through the ReLU. Remember, we already discussed this idea of the ReLU that, and I gave you an example of how it worked just to make sure that our predicted value is always greater than a minimum. Okay? So this is, you could call it penalized undershoot or something like that. Okay? So this is essentially what's so great about this is that if you understand that softbox, then that's what this is. And then you add the loss here. So you have a loss plus this times the weight, again, that we are indicating for this. However, what you might have a problem here when which is what I was saying. Sometimes it may just be better to do everything with this lower and upper bounds because here you do have a little bit of you're controlling the minimum, but what if you overshoot too much? You know what I mean? Like that overshoot could be excessive. So in that case, this is essentially like adding the upper bound of the softbox, but just instead of like how we've defined it before, you have a separate parameter called overshoot that you can play with. So if you notice here, what we do is we take y target, which is the same as this y target, plus this overshoot margin. So now it's like, okay, I want everything to be greater than 250, 100, but don't overshoot it too much. So maybe the overshoot should be equal to 300, 300, 300, for instance, something like that. So you can use this parameter to control that as a safe upper. And then it's just the exact same softbox penalty. Notice we use the ReLU, but now Y-pred is here minus the safe upper because remember, we invert these values, right? So it goes less than, center, center, greater than. So that's how we have the values. And we just calculate the weight, add it to the loss, and that's it. Okay? So mask 2 and mask 3 are essentially the same one. Just that here you control this a little bit differently. And it's the exact same softbox penalty that I had discussed when we did this one. So you remember this whole discussion. Okay? So now let's look at the third case. So let's imagine that the mask is 3 for any one of these. Because remember, 3 can be this one, right? So 3 could be that one. And for that variable and the output, A, you want to use this if statement. So this one is literally almost this one. Just notice that now we're going to use the pre-calculated lower bounds and upper bounds that we had identified before. Okay? So we're just going to use those, which we calculated in the previous lecture. And notice that it's always I because we're focused in the loop. First iteration, we focus on A, then B, then C for this vector of 3 and the outputs. So this is the bounded range, or within range. So I just assigned it to A and B, so this is easier to see, but you can see this is a standard function. Torch ReLU again, that really nice trick. The lower bound minus the pred, and then the pred minus the upper bound. And that gives you essentially the loss function for being within range, the classic example. Remember, again, you multiply it times the weights. That just indicates these are the weights that we discussed over here. You can play with these to figure out where you want to give more strength, where you think your model is underperforming, etc. So this is very experimental. So once you do that and you iterate through the for loop, you have gone through A, B, and C, you've accumulated all of it in the loss function value. And then that loss value comes out here. And what you do here quite simply is you just do another regularization. We discussed this before, where you take the whole Y-pred vector, square each value, sum it, multiply it times some parameter, and then add it to the loss. And that's it. And that is essentially is the loss function that you can use for NIO. With a simple tweaking of your code, I'm pretty sure you can merge mask 2 and mask 3 into something that's a little bit more elegant than what I have here. I just wanted to have more, something that's, a little bit clearer for teaching purposes, but certainly your code can be much smoother. Are there any questions on this constraint loss function? All right, I'm not hearing any questions. So let's go ahead now and we're going to, we finished the constraint loss function, okay? So let's move on to the next example, which it's going to be, so we did constraint loss, parameters, constraint loss. This is just information, notes that you can put in about ranges and things like that. Variables. Right, so now I'm going to use, I'm going to redo the clamps just to make sure everything is good. Remember, clamps is inputs and outputs. Vectors of 7 should be clear. So just run those just in case. Okay. And now, guess what? That's it. So we've made it now to the training loop. Remember that the training loop is just an iterative process where you kind of go through, you're going to start with random values for Z. You train it, going through the forward model. And then eventually you finish the epochs, and hopefully you have a good value for your input. So let's copy the training loop. So that should be this one. All right, so let's break it down. So we're going to do a for loop of 200,000 epochs. So notice this is a lot. 200,000 epochs. So for step in range epochs, so we run through this. Notice that the optimizer is optimizer infer. We zero it out. Then notice I'm going to call the vector of x, which has the values. Remember, the values that go into the model have to be in the correct ranges, not standardized, because the model standardizes it. So it's going to be like natural gas of, 2,500 tons, temperature, 500 Kelvin, something like that. So they're not standardized. The model does that. So we give it Z, right? We give it our Z that we created at some point. That's our parameter that we're trying to optimize. And we are previously discussed in part 1 of this. We covered the get x from C lambda function. It takes inputs and everything, right? It's got inputs, so clamps, I should say, and so it produces an x vector. That x vector, which is 1, 7, will go into the model here. Now, one thing I want to say that I wanted to say before, and I may have forgotten, going back to the constraint loss function, notice that here, this, the values are 0, I. So I is A or B or C, but what is 0? Well, remember that we're doing things in batches, right? So even though the batches are just 1, so I'm just grabbing the first one. Now remember that this code, you may want to do batches of 32 for some reason, because your application actually makes more sense that way. If you do that, be careful in your code to change this to reflect the size of the batch. Because if you don't, what could happen is you have 32, but you're only grabbing like the first one. So this is something in my code that is kind of like not great. I would recommend that you just, make sure to make that change. Okay, I made this just for one value. So I kind of hard-coded this a little bit like that. But I do make the note. Please be aware of that. All right, going back to the loss function then. So we give it Z, 1, 7. The C is the thing that's being updated, right? The only thing, because the model is frozen. So the weights of the model are frozen, but C has requires grad set to true. So C goes in into get X from Z, and that produces X guess, which is 1, 7, which is the input and not standardized that goes into model. What was modeled? Remember, model is just our forward model that we've already, in step 1 of NIO, we've already trained, and the model is, a trained model. Remember, this is trained exactly how you train any regression problem. Okay, so now you give X to the model. The model will predict. Remember that the model predicts Y-pred real and Y-pred scaled. Right? So scaled is going to be for optimization. Y real is so that when we're trying to predict, we actually have values in the correct ranges. Remember, these are vectors that are 1, 3. 1, 3. All right, now notice that our loss function over here, loss main, takes in constraint loss, which is the function that we just defined here. Constraint loss. And so constraint loss takes in as input Y-pred scaled. Do you see that? So which is this one, Y-pred scaled. Okay. It's going to have target output, where target output was defined here. If you remember, when we set up the upper bounds and lower bounds of our model, we also defined target output. Remember that those are scaled already. So you have to always make sure to print those values out to confirm and double check and so on. So in this case, that's target output. Constraint mask, that's the mask, which we've discussed already, which is this one. This is the weights. So constraint mask is this one that controls the if statements 2, 2, 3. So you can take a look at that. Overshoot margin that we discussed, you have to kind of play with this value, but this is your overshoot margin, kind of like an upper bound that's more independent that you can play with. Constraint weights, like I said, constraint weights controls the importance of the variable. So constraint weights was defined here as 1, 3, 1. So essentially we care more about the middle variable. That's the one that gets the most importance. Okay. All right, and that's it. So that is the law. So every time you're doing this in the training, all of these are going to get calculated as discussed in this one in constraint loss. All right, and that's it. That calculates loss main. However, you can see that constraint loss consists of softbox penalties. That's essentially what it is, because we've already defined the theory that a soft box penalty essentially looks like this, right? Which is in our constraint loss. But we may actually want to have yet another constraint, or softbox penalty for the input. So remember that this softbox penalty and constraint loss is for the outputs, right? So that we can keep the outputs within certain ranges. But what about the inputs? We may also want to keep those inputs as part of the optimization. So we can have that one. Remember that we're predicting X guess here, right? And essentially then we can provide the clamp min, clamp max, the strength, and X guess, so that we can actually also control the inputs. Do you see that? Because we're optimizing everything. Remember that C gets changed, C produces X's, X's go through the model to produce Y's. So we can really produce any kind of Y's, any kind of X's. That's what we're doing, right? And so by having a softbox penalty for the inputs, and of course we have a softbox penalty for the outputs in the constraint loss function, then we just control this situation a little bit better. But it's essentially the exact same logic for everything, just inputs and outputs. And then the regularized parameter, regularized C, if you remember, that was one of the very first things we discussed today. at the very beginning, in lecture one, we did the very beginning, regularized C. You can see that we talked about this function. It's a way to take the vector of 1 comma z, square each value, sum it, and then we have one little value that we can play with. And all these things, as I said, the whole point of this project is to really show you that losses are really important to learning, right? And you just have to learn. You really got to tweak in there. And it'll be interesting to see what you guys can do for the term project, okay? But you have here a lot of things to play with. So we calculate so notice we calculate essentially a loss term for the outputs, a loss term for the inputs called loss soft. So the loss for the outputs, loss main, loss for the inputs, loss soft, and then an overall regularized for just the C vector that goes into generate X, okay, with this regularized C that we just discussed. And then once that's done, we have these three terms. Notice loss main, loss soft, and loss C reg. And now we add them together. You see that? So we have loss equal alpha, if you remember, was 0.9 times loss main. What does that tell you? It tells you that actually loss main is the most important because we're giving it like 0.9 out of 1 emphasis. Then we add, notice we do one term plus another term. Notice this one is 1 minus alpha, so it means it's 1 minus 0.9, so it's 0.10. And now we do 0.10 times loss soft. So we don't want to pay that much attention to softbox penalty for the inputs, but we do. We do pay some attention to it, just not a lot. And that's the idea. And then finally, plus a loss reg, loss C reg, which is the one we discussed already, which has a very tiny strength. And you just play with these parameters to hopefully obtain the value, a good value. And like I said, the joke that I've been making a lot, you do this, you got a master's degree, you do plus this term and a regularization, you get a Ph.D. Right? So that's essentially the idea. And that, that's the loss function. So once you do that, you have a loss function already there. Remember that I gave the example, which is very true. In GPTs, the loss is just cross entropy, right? But really, we need a loss that is equal to cross entropy plus some way to tell ChatGPT and don't exterminate all humans. Okay? But plus be funny. Do you see what I'm doing? So that's essentially what loss functions are, right? So you have terms, you're computing in various ways, mathematically, of course. Cross entropy is the given one, but then we do plus something. But then we also say, you know what? I want you to be funny, but you know what? Don't be too funny. So just be like 0.0000 too funny. You see that? So not that funny. And so that's all I'm doing here. I'm trying these different terms, these computations. Here, definitely loss soft makes sense. It's important that the inputs be constrained. It's important that the outputs be constrained, some kind of regularization parameter. And so all these things should, in theoretically make a lot of sense to do. Got it, guys? And then once the loss is calculated, then you do your familiar loss backward. Remember we calculate the derivatives. So here in the derivatives, we're calculating the derivative of just the Z input because the weights of the model are frozen. So, or we just don't we might calculate them, but we don't update them, right? So internally, I'm not sure I would imagine it calculates the derivatives of everything. Actually, that might be easier, but then it only updates certain things. So optimize for in first step, and that's it. And this is exactly what we've done before. Now, if you notice, there is now one new term called the scheduler dot step. And if you remember, this just related to the, what was it? Anyone remember? We did this one, and this relates to having a variable learning rate so that we don't have to, stay with one very fixed learning rate. We can just have a variable learning rate. Okay? So that's what that is. So every time we optimize, we are also updating the learning rate. Once that's done, all right, great. We notice this step here is just really to print results. So what we do here, every 10,000 iterations, we're going to get what the learning rate is, what the current learning rate is, as it's being modified, and then we just print it out so that we can view it. Also here, as the model's training, so every 20,000 iterations, we're going to print the value. So we print Z, X guess, the target output not scaled, Y-pred real, Y-pred scale, target output, clamp min, clamp max, the loss step, etc. So essentially so that we can view the results, but you can print out more things. So if you notice now, what I did is I clicked on the little button here. So the model is now training. Okay? Doesn't take that long to train. I'm not using a GPU or anything, but you can see we can analyze the output. Yes, any questions? Okay, so we analyze here the output as we're training, optimizing. So we see the C parameter. You can see the values of the C parameter, right? These values, not very meaningful, but when they go into the C function, okay, 135, 105, 24, 1389, 208. This is actually the thing that we're trying to find out, right? What is that input? The target is that the value should be greater than 70, 1800, 2600. If you look, Y-pred real is actually 100. So it's now 547. Do you guys see that? So, but we want it to be greater than 1800. So this is not correct, right? This output at 547 is not correct. This value over here at 2059 is also not correct because we want it to be greater than 2600. The only one that's correct is this one. It's 100 and we want it to be greater than 70. Any questions about that? So that's the idea. So notice this one is correct, but 547, not over 1800, that's bad. 2059, not over 2600, that's bad. The good news is we're still in the very first iterations, so let's see if that improves. This is just a scaled version, so you can look at the values, scaled values. And then this is the clamp min and max, which helps you to put this one into context. So for instance, the inputs seem to be, if we look 0 to 0, 0 to 200, so this one 0 within 0, 135 within 0 and 200, 105 between this 0 and 200, so that's good. 24, yeah, within 21 and 32. This one is 0. 1389 between 1300 and 1500. And 208 between 150 and 250. So the values are within the input ranges, but just the output hasn't produced the desired outcome. So 547, 2059. The learning rate, you can see the loss, sorry, the learning rate is 0.03, so it's printing it out. 0.03 still, and then the loss value seems to be 21.32. here. All right, now let's try the next iteration. Notice that now the loss has gone down quite a bit to 0.007. So that's good news. Let's take a look at the x value. So this is the input value. Now let's take a look at the output value. Where is it at? So notice here, we want 79 to be above 70. That's correct. That's good. For this one, we want 2160 to be greater than 1800. So that's good too. And we want 2700 to be greater than 20. So there you go. So it's starting to get better, right? But because it's optimization, we want it to really become as good as possible. So that's where the loss function would come in. If we look at the input now, 53 is within range, 23 is within range, 30 is almost out of range, but still within range, 1444 within range, 210 between 150 and 250, so within range. But the loss, you can see, has really gone down. I actually skipped one. And if you notice, this one was the one that was bad at 547. The next one was also not great. Oh, no, it was good. 1948 is greater than 1800. So that's good. So essentially, really quickly, it got better. But I feel like this value 1948, which is very close to where we wanted 1800, here is getting too far away now at 2160. This 91 is getting away from 70. Do you see that? So it seems almost like these values are better than these values. Now, are they both correct? Yes. So my loss function then may not, while it's correct, it's leaving some money on the table if it keeps doing this. So there may be a correction or two that you want to do. And that's exactly the fun part of this project, right? That you guys will play with these losses to try to figure this out. Okay? All right. So we keep looking. So it's training. I think it's still going, actually. Let's see. Yeah, so it's still training. It's supposed to do about 200,000 iterations. Let's see where we are. So it has done 130,000 iterations so far. Let's take a look at this output. Look at the learning rate. So the learning rate was how it has changed, right? So it was 0.03, then it became 0.015, 0.015, 0.007, 0.003. So notice how it's getting smaller. Okay, so let's take a look at this one. This seems to be the latest. We're about 60% done. Learning rate 0.003. We've got our input. This is the thing that we're trying to optimize for. Let's take a look at these outputs. Ooh, look at these outputs, guys. Look at this vector. So we want it to be above 70 is 82 and getting somewhat, before it was 79, so that's not bad, the best one. Look at this one. 1800, it is at 1886, very close and above, so that's correct. And then 2600, 2650. So definitely better than this situation where we had it at 2160 over 1800. Now, this one is really nice. Do you see that? And so sometimes you might want to keep, even though I didn't do that in this code, you might want to keep track of like a log. You know how you did your checkpoints and you kept track of best results, and really you did a really great job in homework, the LLM. Now you can probably keep track of these, and then if you think these outputs are the best given this constraint, then this may be the best input. Okay? Because the problem with this technique is that I don't know what epochs should be, right? So I just set it as 200,000. It might be good to print those results so you can do a graph, and that'd be something nice in your project if you do that. But yeah, that's the idea. So you want to maybe keep track of those values and eventually print out the best results. So here you can see actually the values are starting to go up again, 90s from 70, 1928 from 1800, 2708 from 2600. And some might be going up, others might be going down. But yeah, that's essentially the strategy. They're not wrong given my loss function, but it seems like my loss function could be a little bit more optimal, and definitely saving like these checkpoints and picking from the results may also be a good approach. So I think this finished now. Still going, but I think it's doing the last iteration. Oh, it finished. Okay, here we go. So, it finished 200,000 iterations. And if I just want to be lazy, I'm going to go with the last result because I didn't record anything else. So let's take a look. So notice that the learning rate ended up being 0.0018. The input is this. Now notice the output. This ended up being a little higher than other ones, but it's still correct. So we wanted 90 to be greater than 70, 1928 to be greater than 1890, and we wanted this value actually to be, if we look at the mask, I think we want it to be in a range. The mask for that one was 3, and so 3, and the upper bound would have been 2,800. If you guys see, between 2,600 and 2,800. So let's see. So our value, yeah, 2,700 is right in the middle of 2,600 and 2,800. So I'm looking at this value, 2,708, which is in between 2,600 and 2,800, perfect. Or these values, which are greater than 1,800 and 70. Now, as I said, you guys, this is just one example. I could have done all threes for the mask, 3, 3, 3. I could have done all twos, 2, 2, 2. I do think within bounds is the best, but it just depends on the information that you have available. And that's why I wanted to give you some options. Okay. So this is our output, which is correct. So therefore, you now can look at your input, and this is the optimized values. So your answer is a vector of 7, which is 0, 60, 33, 29, 0, 1,433, and 204. If we look at these values in the clamps, we can see the first one is zeros. 60 is within 0 and 200. 33 is within 0 and 200. 29 is within 21 and 32. 0 is within zeros. 1,433 is between 1,300 and 1,500. And finally, 204 is within 150 and 250. So there you go. That is your final answer. Notice the loss was 0.006, so it got optimized. And that's essentially the whole process of NIO. So now I have this little nice code here just to kind of print the final results. So you grab this one. Okay, so we set the model now into eval mode, the forward model with the frozen weights. We set the grad to torch no grad, so nothing gets updated. Our C value, remember, is what we optimize. So we have finally arrived at a nice C value. So we plug in C into getX from Z, our lambda function. That gives us our final output, sorry, our final input, X. So notice final input X. Final input goes into the forward model that produces our final output, which is scaled, and now we can print these out. So we've got the shapes. Remember, vector of 7 goes in, vector of 3 comes out. Okay, so that's good. All right, good. And then now we want to just print all the results, which we've already looked at them, but we can I ran the input through the model, right? Final output. So I take out target output not scaled. This is our target, clamp min and max. The final input and the final output. So actually, this is so our values are 89 when we ran C through the model, not the last iteration, because remember that these iterations are just actually training Z, right? They're training Z, but then we ran the Z through the model, and it gave us that the value is 89 to 70, which is a little bit better, I think, because our final one was 90 here over 70. But this one is actually 89. So that's nice. So this value is 89 is greater than 70. 1932 is greater than 1800. And 2684 is between 2600 and 2800. So yeah, perfect. So our final input, our result now, inputs that satisfy the constraints is that one. So this is actually your operator now comes in and says, okay, I want to produce, let's say I want to produce this material, A, B, and C, where A is 89, B is 1932, and C is 2684. So what do I need to do to my 7 inputs, my 7 knobs? So your knob 1 is 0. I'm going to set knob 2 to 60, knob 3 to 34, knob 4 to 29, knob 5 to 0, knob 6 to 1432, and knob 7 to 203. And that's it. That's the whole process, the whole point of this approach. So I ran it, and there you are. So I think what's left here is I just have a couple of things, but essentially this completes the whole logic. Like that is essentially what we're trying to accomplish. I just have a few more utility things. So let's take a look. So I have this piece of code here, which is a quick way of telling me if something broke the constraints. So you can see here, I print out final input again, final output, target output not scale as reference. And then I just say if final output is less than target output not scaled, then there's, I have something called violations, right? And so if violations.any, then print final output violates constraints, and violated constraints, and I have it's like a Boolean type of a variable, else all constraints have been satisfied. I double check everything, your results always. I just did this kind of quick thing, but I may have made a mistake. And then the final output, you grab it. And then there's some specific things, like if a specific variable is greater than 2100 and you're really concerned about it, then, this variable is too high, unphysically high, warning, the reactor is going to explode, something like that. So you want to help yourself. But in this example, we've already checked numerically, but all constraints seem to have been satisfied. Do you guys have any questions? No questions? All right. Finally, nope. All right. Good. All right. So finally, you know, when sometimes I've used this, and I have to like try run it multiple times. And that's because, sometimes it just doesn't converge to the right answer. So I essentially created this function, search or try several times to see if you can find an input. So essentially it's this little function here, which you guys can try. I did try it. I think it does work. Although I don't usually use it because the model has worked just the way I have it. But as you can see, you essentially run with retry. You're going to give it all the parameters that we previously defined. You're going to call it, you're going to run several retries. So 4 attempt in range retries. And essentially you're just running the whole code again. So notice you take cinit, you make it into a parameter which requires grad, you tie it to the optimizer. Then you're going to take a maximum number of steps, right? Like in the loop, like our epochs essentially. And then you zero out the get grad, get z, gives you X guess, run it through the model, and then we just do the constraint loss, soft penalty, regular. I mean, it's exactly the same thing, but in a way that you can run it multiple times. You calculate the loss, update, and then the key thing is you have to evaluate in here. So you give C, get X from Z to produce the final input that goes into the model to produce the final output, and you do the violations thing. You do the violations thing, the logic that I just did before, violations. If no violations, you'll have something like a whole bunch of print statements, success, and it returns that, if no violations, then it means you found an input. So at this point, you're good to go. So that's why there's a return to end the function and provide the result. Else, it just keeps retrying, no feasible solution. And then after a certain number of attempts, it just, does, no feasible solution. So it's essentially the same little code, but just rehashed. Okay, so we can run this one effectively by just invoke. And this is the last piece of this code, by the way. If you look, there's nothing else. So here, I usually leave this commented out because I don't want to accidentally run it, but you can see here it's got all the parameters. We run it. It's taking everything that we've defined above this. It's going to try 5 retries. And it should at some point, well, it's doing 1 run. And I think what's going to happen, hopefully, is that on the first run, it'll finish. Let's see. But if it wasn't able to finish, then it would say attempted something, now retrying. This will take a while, so it'll take as long as this took. Oh, you know what I can do? I can just reduce the number of, let me do that. Hold on. Please stop. Okay. So instead of doing max steps equal 200,000 as I did before, let's just do 2,000. Right, so that should run faster. And we know that 2,000 should be good enough for this example. You can see actually with not enough, it failed. It's retrying. So it's not able to meet the constraints. Okay, so this is a good example, actually. I didn't think of this, but actually this worked nicely. I wonder if once I give it 20,000, that'll be enough. So no feasible solutions. You can see it finished, but actually it didn't. So now let's just give it 20,000. So it's not 200,000. Let's give it a minute here. Okay. Yeah, so this takes a little bit longer, but I think in the very first one, it may succeed. It's 20,000. Okay, you can see, great, perfect. This is beautiful. So you can see actually here in the first attempt, it met the constraints, gave you the input, and that's it. So you can see we tried it for both situations, and it may be, when you have a problem that's like sometimes it works, sometimes it doesn't. So you might want to leave it overnight or something like that, and then it produces your results. All right, guys, that's really great, I think. I'm really happy. I've gone over what I wanted to go over related to neural input optimization for your term project. So now, are there any questions on any of this?
Sir, I have a small doubt in the NIO topic for the term project.
Yes.
So on
So
speaking
on
of
a speaking of
NIO, so it is generic, right? So if I want to use these NIO concept on any other data set, like let's say for bioinfo data set, so I can do it, right?
you,
With
I
build
mean,
a
I've shown you how to do this, for regression values, but what
yeah.
is an image? What is an image? An image is, if I take, okay, I'm producing a vector of three with three
Mm-hmm.
numbers, but I could produce instead of a vector of three, a vector of 784, right? And
Yeah.
there's no difference there. And then if I take that vector of 784 and make it into a square grid, I essentially have a grid that is 28 by 28, which is an
Mm-hmm.
image, like diamondous image. So technically, the machinery exists for you to generate vectors of three, vectors of 784, make them into images in the input, on the output. The challenge, of course, is going to be the loss function. You see what I'm
Yeah.
saying?
Yeah. Yeah. Got you.
And so that's, you guys doing this term project, you can stay with something very similar to what I'm doing, right? Regression values, like a industrial process.
Mm-hmm.
You can try more or not, or just think of this methodology and then think of how you can generate things. If you notice, we optimize the z, but the z would go into a function, right? Called get x from z. And x
Yeah.
was actually the thing that we wanted. So really, we could train z to go into a function that produces a vector of 784 that becomes a vector of 28 by 28, and therefore that's an image. So the input could be the image, the output could be the image. It's just, it just depends. And obviously, if you have a model, the
Mm-hmm.
model would take those same dimensions. Does that make sense to you?
Yes. Yes.
Yeah.
So yeah, makes
Yeah.
sense.
So generative can be the inputs, the outputs, given that actually the thing that we optimize was that original Z vector. So as we will learn once we move into CNNs and GANs, you'll see that GANs are a little bit similar. They also take in a type of a Z, but that Z is random. They just produce a thing, and that thing, then there's another neural network, like a second one, a classifier that just gives feedback to that produced output, and it says, oh, you know what? Um, this is actually good or bad, or fake or real. And that information back propagates to the original C and so on. So there's similarities there. In this model, there's no second network. We actually just optimize the C given the constraints. GANs have a random Z, but they do have another network. Could you add a network to this instead of all those complicated losses? Potentially. So that's yet another possibility. Do you know what I mean?
Yeah, got it.
Yeah. And so what's coming up next, although we have some lectures left, is I'm going to try to speed up CNN and GANs just so that you guys can see that too, to give you a little bit of insight. But you can just do, for those of you that don't want to explore something that challenging, you can just stay with regression type inputs and outputs for the project.
Uh, yeah, actually, here is my concept. So as I was going through a blog which tells about the protein-protein interactions, and
Okay.
upon reading it further, I came to know that to find the perfect protein embeddings with the ligands. So we could
Okay.
but we could use the concept of neural input optimizations to find out which inputs gives us the perfect output, like the which protein embeddings gives us the perfect target binding. And this
Okay.
this area is kind of the I know it's a complicated task, but do you think this is doable in this very short duration of time?
It sounds right. What I would do is try to simplify that problem as much as possible. Don't, I think it's a
Yeah.
great concept, and I would just start with like the simplest thing you can do with it, just to
Mm-hmm.
show that you can get that to work. And then, if you wish to continue the work later, you can, but it sounds, yeah, from what you said, it
Mm-hmm.
sounded like a good idea.
Yeah, because even though the AlphaFold predicts the protein-protein interactions perfectly, but it does fails to give us the exact structure embeddings inside a protein-protein structure. So what
Yeah.
I'm thinking is, if we could use this NYO inside of the AlphaFold embeddings, then it would be a revolutionary findings, right?
Yeah, I mean, as I said, I would keep it simple in your first iteration, just to
Mm-hmm.
like get and that's good enough for the project for sure.
All
But
right.
yeah, for future work, absolutely. Yeah.
Yeah, yes, sir. So thank you so much.
Perfect. All
Yeah.
right, guys, any other questions? All right, and I know it's difficult because we're in this medium. So we have still 20 minutes. So what I'm gonna do is, since this video goes really well with the other one, I don't want to add other things to it. So I'm gonna end here this video, and I'm going to start a new Zoom just the last 20 minutes from 7:30 to 7:50, and I'm just gonna do one of the other topics that I wanted to do, but NIO is effectively done at this point. So we've covered this. Um, and then maybe in a future example, because I'm not prepared for that right now, I might talk about that paper where we were generating passwords. So that might be something in the future. I might dedicate a few minutes, but I won't go into too much depth for that one. Is that good? So what I'm going to do is I'm going to end this one. I'll post this video as part two, and then we'll start exactly at 7:30, do about 20 minutes, and I'll just pick one of the topics that's pretty simple, but that we need to cover. All right, guys. So I'm gonna end here, and I'll sign back in. Okay.